Hi guys, so today we will be doing a tutorial on Module 1 and more specifically theoretical and percent yield. First, before we delve into anything more advanced than what you've already learned, we'll do a quick review on what you do already know. And these are the definitions of theoretical and percent yield. Now the first theoretical yield is the amount of product that should be created in a reaction if it was done in a perfect setting. Now this is theoretically possible, but actually in reality not possible to do. It's impossible to create a perfect reaction, but it is helpful when determining our percent yield. Percent yield is the percent of product that was created in regards to the theoretical yield. So this is written with the equation of percent yield is equal to the actual yield divided by the theoretical yield times 100%. One quick example is 1 mole of hydrogen chloride reacts with 1 mole of sodium hydroxide, and you produce 0.92 moles of sodium chloride. What is the percent yield? Now, using our formula from up above, we will figure out that you do the percent yield is equal to the actual yield, which is 0.92 moles, divided by the theoretical yield, which is 1 mole times 100, and that gives you 92%. Now going into more advanced stuff, here are some reasons for high and low percent yields. First, we'll talk about high percent yields, which is over 100%. This doesn't really happen all that much, and really realistically only results from impurities in the solutions that you're using. This means either the molar ratio in the solution is not representative of what it actually is, or maybe there is another substance in the solution that you did not account for, which could give you a higher mass. But more likely than not, you will get a lower than 100% percent yield. And there are quite a few reasons for this happening. The first and main one, though, being the transfer of solutions during an experiment. This is because it's impossible to get all of the solution from a container into another container. So say you're mixing a solution and you have to transfer one into the other, there will be always some mass that is left behind, which will give you a lower mass and therefore a lower percent yield. A few other reasons are the amount of time that you give the reaction. This could be you don't give the reaction enough time, which could result in not all of the reactants reacting together and not getting enough mass in your product. Another reason is your products could react again with an external factor that isn't actually in your experiment. For example, say you are producing a pure metal, and after the pure metal is produced, it reacts with oxygen and oxidizes, which could lose your solution, lose mass, and therefore lower your percent yield. In general, though, most reactions have a percent yield less than 100%, as at least in a lab setting, we are using pure substances that are very pure, and it is impossible to do a perfect reaction. It is also said that in lab settings, a percent yield of around 70% is very good. So even if it is lower than 100, it still is really good. Now we'll get into some real-world applications. Now, why would you use theoretical and percent yield outside of the lab? Well, I'm going to tell you. The first application is obviously the lab. It's very helpful to determine how accurate your experiment was. A second and more common or practical use of percent yield is the refining of metal ores to form pure metal. Essentially what this is taking a metal ore or a mineral and getting its pure form by reacting it with something else. So you'll take an ore or a mineral that has a high content in the certain metal that you're looking for and react it with something in a controlled setting, and then you will result in getting your pure metal. Yield percent in metal ore is very important as you're trying to maximize the amount of metal that you produce and therefore maximize your percent yield because more metal means more money for the company. So you start with something like this. This over here is a gold ore. You can see you have the gold flakes and then the rest of the mineral. And then you do your refining process. There are a ton of different refining processes. We won't really get into that today. You can look it up on your own if you'd like. But you do your refining process and then you get your pure gold here with your gold nuggets. Another very important and practical use for the percent yield is the creation of drugs with pharmaceutical companies. This is because companies need to spend the least amount of money possible, which means they need to maximize the yield percent so they can minimize spending and maximize profit. This is super important in the creation of drugs. Say you want to turn an injection into a pill form, you have to figure out what the proper experiments and reactions you have to do to maximize your yield percent, and then that just gives your drug company more money. So we have a couple example questions. I'll give you a second to do it. You can pause the video now. But you're using the carbon monoxide to refine iron oxide with the goal of getting pure iron. Assuming the yield percent is an average yield percent in refining factories, 55%, and you used 140 grams of carbon monoxide reacted with 800 grams of iron 3 oxide, how much iron 3 would you produce? The answer is 102.4 grams would be produced. Now, I'll give you the step-by-step. First, you have to determine what the limiting reagent is. And you do this by dividing the number of moles in the actual reaction over the theoretical number of moles. Now, in this example, you have 5 moles of carbon monoxide, and then you divide that by the 3, because that's the theoretical. And then you get 1.666. You do the same for iron 3 oxide, and you get 5 because there's 5 moles of iron 3 oxide divided by the 1 here in the theoretical reaction. So then you know that carbon monoxide is your limiting reagent. Then you multiply the number of you multiply this 1.666 by the expected number, or the theoretical number of iron 3 moles. So you multiply that by 2 and you get 3.333. Then you multiply that number by the molar mass and then multiply the final mass by the percent yield to get the actual mass in the reaction. And this is 102.4 grams. The next example question, you're coming out with a new drug and you have to figure out what to mix sodium hydroxide with. Your two choices are you have to figure out what to mix with water to make sodium hydroxide. Your two choices are sodium chloride and sodium bromide. And in both cases, you mix 100 grams of water with 30 grams of each possible solution, also with a percent yield of 72%. Your job is to figure out which produces more sodium and what mass of each one of them produces. The answer is using sodium chloride, you will get 14.784 grams, and using sodium bromide, you'll get 8.398 grams. Therefore, sodium chloride would produce the most sodium hydroxide. Now, how you do this is you would take your molar or your actual amount of each solution and divide it by the molar mass, and that's how many moles of each one of these will be reacted in the reaction. You figure out that each sodium chloride and sodium bromide are the limiting reagent in each reaction. You will then take that number and multiply it by the molar mass of sodium hydroxide to get your theoretical mass, and then multiply that by your 0.72 or your percent yield to get these two masses. And here are my sources. Um, I encourage you guys to do more reading on this if you are interested in, and thank you for listening.